So yes, here we are. We are sprinting towards a conclusion. So we're back on topic now. What I'm going to talk about in this lecture overlaps quite a bit with what you've heard before from Bob and to some extent from Kathy. I've trimmed things down, moved things around to shift the concentration here a bit, but we're going to cover over the same areas. The same questions that came up yesterday about what does clustering mean and how do you measure it are bound to come up in this talk, because the charge that Mike gave to me was whence the disk, which is where the disk star is coming from. So this is my perspective on that, and this is somebody who doesn't work on the OB associations, that kind of area, but it's the conclusions are going to be roughly the same as what Bob was saying yesterday, that clustering is something that we need to try and quantify in some physical manner. So what I'm going to do is talk a bit about environments for star formation. I'm going to spend a little bit of time on low mass stars, since that's something that we haven't talked much about, and that's something I actually know something about, and also talk a little bit about the TW Hydra Association, which also hasn't really come up much. I'll talk a bit about, much of this talk is reviewing the LADA and LADA paper again. But in that context, I'll talk a bit about infrared surveys and their impact. And then at the end, I'll take a little bit of time to say, well, what do we do next? So, star-forming environments. We've been through this a lot now. There are dense massive clusters. There are compact smaller clusters like, Colander 39, Lambda Ori. Dispersed OB associations, and then low-density star-forming regions, which Taurus seems to be the classic, possibly the only example. And the question is, so where do most stars in the galactic disk now, where did they form? So OB associations, we've covered this ground a long time before. Adrian Blau characterized, what is it? The seminal paper or whatever in describing the characteristics of these objects was from Blau, although the name was Kapteyn, Jacobus Kapteyn was the one who identified them by that name based on the presence of helium stars, that is, stars with helium absorption lines. And then ages were estimated as about 10 to the 7 years based on their having OB stars in the 1930s, 1940s. The space distribution of these objects was used by Morgan, Sharpless and Osterbrock to map out spiral arms. So this is just XY plot. I guess actually no, this is longitude, galactic longitude, and plotting up the OB stars and showing that they actually form into the spiral arms. So the structure, we've covered this before quite a bit. Low contrast with background. It's very difficult to set clear boundaries. The lower mass members within these associations are still not well defined. Since they cover such a large area, doing a thorough survey. I guess at the start of the meeting we were saying Kathy's going to explain everything. Now we're saying Gaia's going to solve everything. But Gaia should actually add in the low mass members in these associations. And then there's substantial substructure, like the trapezium cluster in Orion, and subsystems can show quite an age range. Bob showed this diagram. This is from the it was Anthony Brown, Tim DeZu's work from the Hipparchus, studying the SCO-SEN association. One interesting thing that I came across was a paper recently published, or I think it's an AstroPH, by Eric Mamajek's students, Pico et al. They find different ages. They actually find older ages for these subsystems. Upper SCO, they still find the youngest system at about 11 megayears. But these two, they actually switch. They're basically Upper Centaurus and Lower Centaurus. They find roughly the same age, 16 or 17 megayears. So that shows there's still some dynamism there in terms of exactly how old these systems are. And in many ways, that ties back to matching against theoretical models, which are still in the state of flux for massive stars at these young ages.
Neill, are those turnoff ages or are those the low mass star?
I think those are turnoff ages. I don't remember exactly, but
low mass stars actually.
They are low mass stars. Okay. So that may then just be a mismatch between the isochrones for massive stars and low mass stars. One of the nice little pitfalls you can fall into here. Different modelers produce different answers.
Remember, the ages that I showed were actually kinematic expansion ages, so there's really three
Right.
ages going on here.
Okay. So we don't really know how old they are, but they're young. I stole this from one of Mike's slides because it's just a beautiful picture of the Orion Star Forming Association. The density maps there are for CO and CS, so radio measurements of dense gas through the region, and then it's dotted with star forming regions. This then is that same region turned into star formation regions. These are the regions that were identified by Blau, Orion 1A, 1B, 1C, and actually the trapezium pegged as 1D. These are the ages that Blau estimated, 12 to 4 billion years, and then the modern estimates that tend to be based on lower mass stars are a little bit younger. But essentially, there's the same picture there of a range of ages within this large association. So now I wanted to go back and talk about the low mass stars and how they fit into this picture. All of these diagrams that I'm going to show here are from theoretical models calculated about 1997 by Adam Burrows and his collaborators, but this is basically, they're still a reliable indicator of how low mass stars behave. All of the plots have age along the bottom axis, logarithmic age from 1 million years down here, 1 billion years. And then this diagram here is the central temperature. So this is the evolution of central temperature in stars with a range of masses stars and brown dwarfs from 0.11 solar masses for the most massive object down to 0.06 solar masses for the lowest mass object on this plot. Basically, this is energy from collapse. As you collapse, you heat up the core temperature rises. In order to establish hydrogen fusion, you need to get above a temperature of about 2 million degrees. And you need to stay above that temperature. So you can see for a 0.11 solar mass main sequence star, it gradually climbs up, and it's a substantial time it takes. I mean, it's 200 or 300 million years for the star to eventually establish a stable temperature in the core for hydrogen fusion. When it does that, the temperature settles out and it continues hydrogen burning. As you go down in mass, well, the smaller mass objects, there's less energy, therefore they don't reach the same, they reach lower temperatures, lower maximum temperatures, the same time scale. When you get to this is 0.085 solar masses, the red line there, 0.08 solar masses, the central temperature turns over. What's happening there is that the star is partially degenerate. You're collapsing to the extent where you hit degeneracy pressure as a sink of energy. So some of the energy from collapse goes into preventing degeneracy. That's why the temperature rises and then falls. You've still got a collapsing object. And that's why you have brown dwarfs. If you didn't have degeneracy, then you could have stars as small as you want. But degeneracy stops stars collapsing at a certain point, essentially at the radius of Jupiter. In order to hold up, you need energy. You suck that energy from the collapse. And that's why the temperature in these low mass objects, the 0.075 solar masses, is generally regarded. These are all for solar abundance. This is the transition mass between stars and brown dwarfs. At this point, you get something that actually it maintains stable hydrogen fusion for a matter of 1 billion years or so. But then degeneracy wins, and you, as Adam Burrows says, you cool like a rock. If you're 0.07 solar masses, you never start hydrogen fusion, and you just cool like a rock. So this is what's driving the surface behavior, the overall behavior of brown dwarfs and the separation between brown dwarfs and stars. What does that mean for observations? Yeah, actually, I guess that's right. I misspoke. It's 3 million degrees for hydrogen fusion. It's 2 million for lithium fusion. This is just the size of these objects. Every brown dwarf is basically this. Actually, from low mass stars down to Jupiter, everything is just about the same size. From about 0.1 solar masses down to Jupiter, everything is the same size because it's all established by degeneracy, not by any kind of what do you call it? Thermodynamic equilibrium within the star itself. So, what does that mean for luminosity evolution? So this is log age luminosity from solar luminosity at the top, down to 10 to the minus 6 solar luminosities here. And again, an array of tracks, 0.15 solar mass star, 0.08 solar mass star, the 0.075 solar mass transition object, and then a 0.07 mass brown dwarf, down to, this is a 9 Jupiter mass, or 0.009 Jupiter mass object down here as the lowest mass. And you can see that the luminosity changes rapidly with time for brown dwarfs. The change in luminosity for the in this section of at the earliest stages is basically it's both a change in temperature, but mainly it's a change in radius. The star is collapsing in size, and it's the size of the object that's determining the luminosity there. But everything in this mass range starts off more luminous than 10 to the minus 3 solar luminosities. So brown dwarfs are luminous at the start of their career. And just to focus the attention, this is the part that we're looking at when we're talking about young clusters and associations. This is why people look for brown dwarfs and young clusters and associations, because they're bright. What happens in the temperature plane? So 3,000 degrees, 2,000 degrees, 1,000 degrees, and that you can divide that into T dwarfs, L dwarfs, and M dwarfs up here. So everything starts off as an M dwarf, and I'll show you. I'll just run through the spectra quickly after this, just to show you what they look like. For the first 10 million years or so, the temperatures this is 0.02 solar masses. Above that, the temperatures are fairly flat. So you saw that the luminosity is decreasing over that same range. That's because the radius is decreasing. The temperatures are pretty much constant in there. Then after about 10 million years, things start to fall off. The main sequence stars settle into a stable configuration on the main sequence. So they have a constant luminosity. And being M dwarfs, they're going to be around here for what's beyond giga-years, whatever. They'll be the last thing standing in the galaxy. Brown dwarfs just disappear off the map. So that by an age of 10 billion years, a 0.009 solar mass object, or a 9 Jupiter mass object, is down at a temperature of about 500 degrees. So I guess the crucial thing to take from this is that brown dwarfs, stars you associate with a constant spectral type, essentially, on the main sequence. You can set up a relation between luminosity and mass for a star because it sits at a stable configuration for a long time. Brown dwarfs don't do that. They evolve on relatively short timescales in temperature from M stars through L dwarf, through spectral type M, through spectral type L to spectral type T. So they change rapidly in astronomical terms with time. What do they look like? So that, just a set of pretty pictures. This is blue and visual for early and mid-type M dwarfs. So spectral type K7 down to M5. As you move down the spectral sequence, the main thing that happens is you see molecular bands sit in, particularly titanium oxide. You can also see that when you get, this is chromospheric activity here down in the coolest M dwarf, calcium H and K, and then the hydrogen Balmer series in emission. Calcium hydroxide is something else that switches on. Where is it? There. So you get complex molecules starting to form in the atmosphere. As you go to later types, this is now the red part of the spectrum. It's the red part of the spectrum because there's not really very much flux down here. The whole temperature, the change in temperature is moving the flux to redder wavelengths. So you start to see sodium lines, potassium lines here, the titanium oxide bands, the calcium hydride band. TiO gets much, much stronger and effectively saturates. Vanadium oxide sets in around about spectral type M7. It's another there. The vanadium oxide there gives this characteristic V shape in the band head, around about 7,200 angstroms. And the hydride bands also start to become strong. Then there's the L dwarfs. This is one of the big shifts over the last decade, where we've pushed to much lower temperatures than spectral class M. This is a suite going from spectral type L0 to L8, just to give you an idea of how things change. And this is just zooming in. The main thing that's happening in these atmospheres is they're becoming cool enough for titanium and vanadium and other refractory elements to actually solidify as dust. You form dust in the atmosphere and it actually gradually settles out with time. So when you take titanium and vanadium out of the gas phase and put them into solid, you remove TiO and VO as opacity sources. So TiO and VO bands become much weaker. The atmosphere actually becomes much more transparent. The hydride bands get stronger, and that's a kind of pressure effect. Hydride bands are stronger in dwarfs. They become even stronger in these atmospheres because they're more transparent and there's a higher pressure. Because the atmospheres are more transparent, you get things like this. This is the potassium line here. This is the potassium line here in a late type L dwarf. It's basically the same width as in a white dwarf. And it's the same reason it's the same width as in a white dwarf, because you're seeing deep into the atmosphere, you're seeing to high pressures, and it's pressure broadening that takes a 2 angstrom wide line up there and puts it into a 1,000 angstrom wide line down there, which I think is pretty cool, but I'm biased. You also get a weird element. I mean, cesium, who would have thought you'd see cesium, rubidium, a chromium hydride as strong lines in cool objects. And the reason why you see that is because everything else is being taken out as dust. And then once you get from spectral class L to spectral class T, there's two things that happen. The atmosphere becomes even more transparent. Dust essentially drops below the level of the photosphere. And as that happens, well, I guess this is the infrared spectrum for M and L dwarfs. You're basically dominated by strong water absorption between, so the J, H, and K bands. They were picked because there's water absorption in Earth's atmosphere. There's also steam absorption in the cool dwarfs. And as you can see, going from this is L0 down to L7, the H section of the spectrum gets squished. And that's because steam bands are broadening on either side of that and eating into it. This band head here is carbon monoxide that appears. And then there are also lines due to potassium alkali elements visible there. The transition to T comes when, as I say, the atmosphere becomes transparent, the dust settles out of the atmosphere, and it's most prominent at infrared wavelengths, where you get strong bands due to methane that come in and essentially chop off large sections of the infrared spectrum. So, and this is actually something that was predicted back in 1964 by Tsuji. Despite that, for 30 years after that, everybody searched for really, really red objects in the infrared. But they're not really, really red because you've got the methane bands taking away the flux at the H and K bands. So when Gliese 229b, the first really established brown dwarf, was discovered, everybody was surprised that it had blue infrared color, and they shouldn't have been because Tsuji told us back in 1964. Okay, so that's the spectral evolution of low mass objects. So what does that mean for clusters and associations? Again, focusing in on this part of the diagram, because these are the ages you're looking at. It means that brown dwarfs in young clusters are predominantly spectral type M. If you take a 15 Jupiter mass object at about 10 million years, it's about 2200 degrees, and it's only 10 to the minus 3 solar luminosities. So all of the young associations that we're talking about, you're looking in this part of the diagram. And it's basically, they're brighter objects. So I thought I would just run through that since it wasn't something that we talked about before, just to give the background for what we're looking for when we're looking for very low mass objects. And yes?
So how do you use pressure to differentiate between the brown dwarfs and other low mass stars in the open clusters?
It's still a temperature, at a given age, it's still a temperature sequence. So essentially within a cluster, if you order things by spectral type, you're essentially ordering things with the caveat that there might be dispersion in age, and that could be important down here. You're essentially ordering things in terms of mass. It's just the whole scale has changed. But it's also true that for low mass brown dwarfs at a young age, the spectra do look different than old M dwarfs. And that's because the radius is different. The reason why these objects are so luminous is because they have much larger radii. So that when you look at the brown dwarf spectra at this age, you see features in the spectrum that are more characteristic of giant stars because there's a much lower gravity in the atmosphere. So there are spectral differences and you can distinguish. And in fact, that's one way of trying to identify young brown dwarfs in the field, because they will show the hydride bands will be weaker because it's a much lower pressure than compared to an M dwarf of the, or a stellar M dwarf of the same spectral type. So, I should say, I mean, feel free to interrupt with a question. I'm not as nice as Bob at asking people to interact, which means you should not be nice to me and interact if you want to. Okay, so that then is an introduction to something that we've, I think it's been lurking out there, but we haven't actually talked about it directly yet. And I'm not going to say much. But the fact is that within the last decade or so, we've identified several loose associations of 10 to 20 million year old objects in the field. TW Hydrae, Beta Pic Association, the Tucana Horologium Association, Eta Ka, they're all named after the kind of the prototype star in that group. They all seem to they seem to be real moving groups. The age estimates are comparable with the STScI Association, and they're almost all in the southern hemisphere. This is just picking out two locations for the TW Hydrae and Eta Ka groups. And they do tend to be towards STScI, but they're much nearer than STScI. These are things that are 50 to, I don't know, 30 to 70 parsecs away from us. Low mass objects in the field. They have velocities that are consistent with them perhaps originating in the STScI Association, but that link is sort of, it's not been tied down, I would say, but it may be the best guess as to where they're coming from. Just to focus in one misspelled association, it's Hydrae, not Hydrae, never mind. The prototype star in that association is actually relatively low mass. It's only 0.3 of a solar mass. I think it's the nearest classical T Tauri star. It has a large disk. It has a gas-rich disk. It's accreting material. Within that same association, and the age is estimated at 8 million years, within that association there's at least 25 systems. Interestingly, there's almost half of them are binary, quadruple, or triple. So there's a high multiplicity fraction for this system, and it's very dispersed across the sky. But they do seem to have, within the uncertainties, they seem to have very similar ages. The most interesting binary is this object here, 2-mass 1207b, which has a very low mass companion. And this is a brown dwarf. The primary star is a brown dwarf. It's spectral type M8, roughly, but it's probably about 26 Jupiter masses. The companion is mid-L. It's probably about 8 to 10 Jupiter masses. So this is a high mass ratio system. It's also only about 10 million years old. And the companion shows signs that it is actually actively accreting from a disk. So this is something this is a wide, low mass, weakly bound binary that has somehow escaped from a star forming region without getting stripped. There is actually something else. For a long while there was a big problem with this system, because if you took the spectral type for the companion and you tried to estimate a temperature, the spectral type is mid-L, which means you would normally estimate about 1600 degrees. Well, it turns out that that's not the right thing to do for an object that's as low mass as this. A chemical equilibrium in the atmosphere starts to become an issue. You're basically this is where you really actually are tying in from brown dwarfs to planets, because the whole chemical structure of the atmosphere changed. There's a nice paper by Travis Barman who shows that even although in higher mass brown dwarfs, the transition from spectral type L to T happens at around about 1300, 1400 degrees. When you get down to something that's this low in mass, you don't get that transition until you get down to below 1000 degrees. The problem with having the high temperature was that if you then plugged in the values, you would end up with something that was about 3/4 of the radius of Jupiter, which did something bad to degeneracy. So it turns out that you can solve that and get the right, you don't violate degeneracy if you put in the proper chemical equilibrium in the atmosphere. So this really is a case where, we always say this in proposals when we want to observe brown dwarfs, that there's a link between stars and planets. This is actually a case where it's true. And as I say, Travis Barman has a really nice paper on that. Okay. So one other thing to talk about then, perhaps, is forming small stars. When we think of a cloud fragmenting to form stars, the low mass limit within that cloud is usually set by what we call the opacity limit for fragmentation. This goes back to Martin Rees and Low and Lyndon. Basically, it says that you've got a cloud that's collapsing and fragmenting. It's releasing energy. The potential energy transformed to the potential energy is radiated from the system, allowing it to collapse further. The fragmentation will stop when the fragment becomes optically thick. So it traps the radiation, it traps the gravitational potential release within the system and heats up. The low mass limit that's usually ascribed to that limit for fragmentation is somewhere between 3 Jupiter masses and 10 Jupiter masses, depending on composition. These are values for solar composition. But there's a nice paper by Anthony Whitworth and collaborators in the Protostars and Planets 5 that discusses that. But that is currently the best estimate for what's the smallest object that you can form by this fragmentation process, at least isolated. This is not talking about forming planets within a disk, obviously. Okay, now back. I guess we've gone through this before. Where do stars form? I think Bob showed this beforehand, and Kathy may have shown it too. This is from Wieland's work, looking at the age distribution of clusters. And this was just looking at the age distribution and how clusters were being destroyed. This is the argument made back in the 1970s for why open clusters could be the source for only a small fraction of field stars. There weren't enough clusters to provide the numbers in the field. And this, Bob showed this, I think, in one of the early talks, that Piskunov et al. Have gone back and looked at the age distribution for clusters, and the typical half-life is about 250 megayears, a formation rate of about 0.3 clusters per year. Okay, so.
Can I interrupt you?
Sure.
Can you go 3 slides back to the low mass and three Jupiter masses?
Mm-hmm.
Is that also a distinction between planets and stars?
It could be, but I don't think we actually know this number really well enough to say it's a hard limit. But in principle, I mean, if you can really establish that there is an opacity, that there really is a lowest mass that you can form from a collapsing cloud as opposed to forming in an accretion disk, then that would be a distinguishing characteristic. But things get fuzzy down there, and what dogma sometimes tends to enter the picture as to how you draw the line. Some people have said that, well, we should call anything that doesn't burn deuterium a planet. Deuterium burning is around about 13 Jupiter masses. We can't actually observe that. Yeah, Mike?
Just to chime in, you can imagine between that range, 3 and 10 Jupiter masses in a cluster, there could be things that collapsed on their own, as Neill's suggesting, and there could be planets formed from disks that got ejected in multiple encounters, and distinguishing them would be incredibly difficult. If someday we had spectra good enough to get surface gravity information that could tell you whether there was a 10 Earth mass core buried down deep inside that thing, and Neill's the expert on the spectra, but that's pretty tough. So that might be the only way, or velocity dispersions might help a bit too, but there will always be an overlap probably.
Right. And also, yeah, this is the ideal. This is the considerospherical cow approach. This is something that's collapsing by itself in complete isolation, which we know happens all the time. So, okay. So clusters. So let me zoom. This is mainly just to say that infrared was crucial in terms of changing our understanding of OB associations and how stars form. I just mentioned this here. The first infrared sky survey. Gary Neugebauer and Robert Layton did back in the 1960s. They took a plastic mirror and they coated it with aluminium. And then they observed the sky with 8 detectors mounted in pairs, so nodding the telescope, with a resolution of something like 10 by 10 arc minutes. The main route, they found almost 6,000 sources, one of which was the Beckler-Neugebauer object, which I think is probably the first I think that was the first real indication of a massive star forming in a highly obscured region. But yeah, this is not an efficient way of collecting data. But it was the best infrared sky survey until Toomas and Dennis came along in the 1990s in terms of aerial coverage. So the first real embedded cluster that was detected was probably Rho Ophiuchus. And that was, again, a painful single-channel mapping. So you're stepping up a detector across these areas here. I think it's about 100 square arc minutes. And the conclusion from this paper was that there was much more compact clustering than is typical for OB associations. The observed density suggests we're observing a rich open cluster located at the center of the Rho Ophiuchus cloud. This was Grasdal and Strom in 1974. IR surveys then have stepped on from there. Actually getting array detectors was crucial to making real steps in this, because doing things one pixel at a time was really time consuming. And I think this is probably the start of the embedded cluster work from Elizabeth Lada's survey of the Orion region, she covered the NGC 2068, 2071, and then NGC 2024 regions back in 1991 with an array detector. 2,800 1x1 arc minute fields. I think this was a thesis work. I don't remember exactly, but it's the kind of thing you would ask a thesis student to do. Go out there and observe 3,000 fields, one at a time. And of course, it's an excuse to put up a pretty picture of the Horsehead Nebula. And this was then the first large-scale, I think, coverage that suggested, well, it showed that the stars, the forming stars, that the point sources within these clouds were not distributed uniformly. Yeah, so the sources are clearly strongly clustered. That doesn't mean they're in clusters, since we're going to have this debate about what exactly is a cluster. But it's clear that this is not a uniform distribution of sources. And just to emphasize how important the infrared is, this is an I-band image of Lyndon 1630. And this is the infrared image. So no stars and stars. Obvious but true. Okay, well, since then there have been quite a number of surveys. The space-based IRAS, Spitzer, and Herschel going on at the moment, looking at mid-infrared wavelengths, and then Dennis and Toomas have scanned most of the sky. Actually, Toomas is all the sky. Dennis is most of the sky accessible from the south at near-infrared wavelengths. And those have provided a large database for following up. So when I originally planned out this talk, I was just going to step through the Lada and Lada paper, much of which Bob had talked about yesterday, so we can skip through some of these slides. But just to go through their methodology for identifying what they called clusters. So they said the evaporation time for a cluster is going to be 100 times the relaxation time. And the relaxation time is given by this formula here. 0.1 times the number of objects divided by the natural log of the number of objects times the crossing time. And the crossing time, as Bob said in probably the first lecture, is typically 10 to the 6 years. So they set a requirement to look for, identifying clusters, that the evaporation time for what they called a cluster would be more than 10 to the 8 years. And that turns out to mean that in this formula here, if you have more than 35 stars, 35 sources within a particular volume of space, then the formal evaporation time is longer than 10 to the 8 years. So they, in their review paper, compiled a census of local embedded clusters, 76 clusters within 2 kiloparsecs. And this is the diagram here that they came out with it. I think Bob showed a different version of this. So this is, what is this? This is the mass in stars within clusters of different sizes. Am I right in that? Basically what they found was that there was roughly equal mass in clusters of different sizes down to cluster numbers of less than about 50 stars. So at less, they found fewer small clusters within the sample than perhaps they might expect if you just took a uniform distribution of cluster size. And massive clusters they found that were rare, but they accounted for about 50% of the stellar mass. One of the interesting things is that they actually, based on their measurements, they came up with a star formation rate, which was about 1 to 3 times 10 to the minus 9 solar masses per year per square parsec. If you just blindly take that and integrate it over the disk of the galaxy, taking the galaxy as having a radius of 12 kiloparsecs, you actually get ballpark 0.5 to 1 solar masses per year over the galaxy as a whole, which is actually in the same range as various other estimates are giving. So that at least is interesting. And then recently, this has been redone well, not recently actually, around about the same time, Porras et al. Redid the survey and came up with roughly the same answers. So their conclusion was that most stars, 80% of the stars, they said, were forming in clusters, they said clusters, with more than 100 members. So that most stars, they argued, were forming in a clustered environment. So how does this then fit with Whelan's analysis? Well, the argument, this is what was infant mortality are the words that we haven't been using up until now. That's basically what this is talking about here, that the clusters dissociate before they come out into the field. In terms of the internal structure of the clusters themselves, some of them, Lada and Lada found to be what they called hierarchical, that there was a lot of structure in the way that the sources were distributed within the stars. So NGC 2264, they find that to be really quite a complex density distribution. On the other hand, there are other clusters like the Orion Nebula cluster, which have a smoother distribution and a central core of massive stars, which may or may not mean that mass segregation has happened. Okay, let me just skip that. So then this is the destruction, cluster destruction diagram, where taking the number of embedded clusters at young ages up to a few million years and extrapolating into the field and then comparing with the age distribution of open clusters. Lada and Lada concluded that a large fraction of these objects must not survive to get out into the field because just the mismatch between the predicted numbers and the observed numbers. So yeah, I think Bob mentioned this before, that the cluster birth rate they estimate is 2 to 4 per megayear per kiloparsec within the giant molecular clouds, which is a factor of something like 10 to 15 higher than the birth rate of open clusters. Okay, I think we've essentially covered most of this in past talks. So I guess that picture has sometimes been characterized as having two types of star formation. That there are stars that form in a clustered environment, and there are stars that formed in isolation. There's a paper that I came across by Breslin et al., which looks at this in a somewhat different way. This is actually from Laurie Allen's et al.'s analysis of the distribution of sources within several star-forming regions that they put together for the Protostars and Planets 5 workshop. They find that about 20 to 25% of sources within these associations are in relatively isolated groups, and this is the distribution, the fraction of stars within groups that are less than 10, 10 to 30 objects, 30 to 100 objects, and more than 100 objects. And I think this diagram here has perhaps been taken to indicate that there are large clusters and then there are isolated objects, and there's not much in between. But there's a paper by Brescent et al., which I think some of you know better than I do, where they have looked at the distribution of these sources. They've actually taken a larger sample of objects. They've used the Spitzer, the cores to disks, several surveys for young objects going beyond the giant molecular clouds, and looked at the distribution of objects, the clustering of objects. They find a smooth distribution in terms of separations, that from their analysis, there doesn't appear to be a preferred surface density of formation. So they find that, just taking it as, fitting it as a log normal, The dispersion in surface density is about 0.085 in the log. The peak is around about 22 YSOs per square parsec. So they would then argue for more of a continuum rather than focusing so much on the formation of stars in embedded clusters. So what next? Well, some questions that I came up with. What exactly is Orion going to look like in 40 million years? And we see it as a large series of star formation regions now with something of a range of ages. Can we take that forward and evolve it and try and figure out what it would look like? Can we find examples in the field of what that would look like in 40 million years? Similarly for SCOSEN, and then there's an ARA OB1 association where there seem to be objects in there that span a range of 3 to 40 million years. I mean, what are these going to evolve into? And maybe one way that we can try to understand that is by building on the Spitzer legacy surveys, going to larger scale surveys to try and analyze YSO samples to really try and understand what the distribution of these objects is. We need to couple here the infrared surveys with Gaia in order to actually confirm what are young objects. The other thing that we need to do, I think, is look next door. The Large Magellanic Cloud has been completely surveyed by Spitzer as part of the SAGE legacy program. The LMC is basically, it's classified as an irregular galaxy, but I think there's actually strong evidence that it's probably just a low mass spiral. This is the bar of the LMC, 30 Doradus. This is the optical picture. You go to Spitzer and you see, here's 30 Doradus again. There's lots of star formation going on in there. And the advantage is that we're looking at this from outside. We can actually get quite deep into it with Spitzer. We can find certainly the high mass stars with YSOs within the LMC. We can try and figure out where they are. We also have 2-mass data. 2-mass data, everything goes away and you get a nice smooth distribution. The 2-mass is giving you the stellar background. So I think that actually is probably that's going to be, I think, obviously there are challenges in terms of getting down to very low mass objects here, but you have the outside perspective, you have the global perspective. I think that may make things easier than trying to figure things out within the galaxy itself, because how stars form in the LMC really ought to give us an indication as to how they're forming here. Yeah, and then as I'll plug later, JWST is going to be a fine way of probing in selected regions, going to very low masses. So that's basically what I was going to cover here. The infrared imaging is crucial. Young stars appear to show significant clustering within the parent molecular cloud, but it's not clear how that distribution changes as gas dissipates, and further observations of YSOs, I think, are really the way to go. So, thank you. Questions, comments? Particularly on the measuring of distribution of YSOs. Thomas? You don't if you don't want to.
I think a main point in the Brexit paper, well, which is quoted a lot, which is only, I think, one line in the paper, is that you should see structure in the surface density distributions if you would have these two modes of distributed and clustered star formation. But this is not quite right, because you don't. This is based on the argument that you have a very uniform high density region with a sharp cutoff, and that gives you 2 peaks of surface density. Whereas if you have a plumbosphere or some more extended distribution, it will have a wide range of surface densities also for a cluster. So those the field population and the cluster population merge together, and you won't see any structure. So this is perhaps
That is true for the outskirts, right?
that is true for everything. I mean,
I think they did a statistical test where they projected plumbers on a say pretty much homogeneous background, and they did find a bimodal distribution. So
Right, but that background has to be really, really diffuse, really different to what you're putting in. And it doesn't matter what morphology you choose, you may have this cumulative distribution. You can have a very clumpy fractal morphology, looks absolutely nothing like a nice spherical sphere. It gives you a smooth cumulative distribution, as does a Plymouth sphere, as does a King profile. Their point is true, but I don't think there is, a starting region that just looks like a uniform background.
So it depends on the statistical test that you do.
Yeah.
So I think this is something Kathy mentioned too. I mean, surface density is kind of the worst. It's the easiest, so it's the first one you should use, but it's so degenerate. So many different things can give you that, or qualify or correct my statement.
Sorry, I think surface densities are great. But I think the problem with that analysis was really the using a cumulative distribution, which is per se also a good idea. But if you for example plot a Krupa IMF which has these kinks in it, and you plot a Chablis IMF cumulatively, you can't tell them apart. So in the cumulative distribution function, the structure is sort of smoothed out. So what you should do is perhaps look at surface density maps and then perhaps apply some cuts or something like this.
But I guess the point of their paper is that these cuts will be arbitrary,
Yeah.
because you cannot link them to anything physical.
I mean, that's what people usually do for identifying clusters. You make a surface density map, and then you kind of say 3 things or whatever. And then it's a statistical point of view, but not necessarily from a physical point of view. Depending on whether you draw the line, you identify more or less clusters.
Yeah, but you could find substructure, for example.
Sure.
I mean,
So I think this is something we're going to return to, but one thing that occurred to me is that when I was doing my PhD, galaxy clustering was something that everybody was focused on. And there's a whole toolbox of techniques that was used in that field. And maybe, I think we'll probably want to stand up and stretch now, but perhaps a discussion in the afternoon. I'd be interested in hearing how many of those techniques are actually applied to these kind of distributions, because essentially it's the same question. And do you want to say something now, Kathy, or hold it for later?
Just very short.
Right.
The obvious thing to do is two-point correlation function, but that relies on having everything being homogeneous on a large scale, which in cosmology it is. And that's why the mean surface density of companions, which is actually rather closely linked to the two-point correlation function, is used instead, because you don't have to specify what the large scale field is. So I think people in this field have been looking to cosmology, but they have to adapt what they do to the situation.
Anyway, I'm sure this is, so yes, go.
So one comment about that. So the two-point correlation is in statistics a second moment summary statistic, and there's an easy modification to those statistics to take into account differences in intensity. So in cosmology, you would expect to have, even if galaxies are clumpy, the mean number of galaxies in a box has an expected value that's uniform for the whole sky. So Baddeley has created a modification for these statistics to take into account different intensities. So this could be used for either incompleteness, but also possibly differences in structure, like with a cluster where it's clearly not uniformly distributed, but there's a clear difference in the core. But if you can model the core and get the expected intensity, then you can make these modifications to the two-point correlation function. But one of the difficulties is modeling the surface density itself, because errors in that can cause biases.
Bob?
Neill, actually changing the discussion a little bit, but maybe not as much as I thought at first. How does TW Hydra fit into your picture of star formation into the field? I mean, do you see it as it was a small embedded cluster, or do you actually see it as part of this supposedly more dispersed?
So I don't have a picture, but I certainly explaining TW Hydra is, I mean, the convention, the ages fit with SCO-SAN. Presumably you have to explain why it's, as a whole, seems to be, I mean, it has to be moving at something like 10 to 15 kilometers per second to get from there to here. in the time available. How you get a consistent group of stars doing that is not quite clear to me. And some kind of leakage from some kind of leakage from the cluster. The fact that you have these binaries in there suggests that they're not being ejected, because you would think that you would lose a lot of these. Some of them are strongly bound, but most of them are weakly bound. So I don't have a good picture. I think the what's been put forward is that, well, they're about the same age as SCO-SAN. They could have come from SCO-SAN, but why they came from SCO-SAN, I think, is not something that we understand. Maybe it's, unless it's some kind of one of these gravitational perturbations that just pulled off a bunch of stuff. But I don't have an answer for that. And I think we should now take a break.